My name is Ameen Soleimani. I work at Consensus. I'm a software engineer there. My primary focus is on state channel implementations. So actually, before I get into the agenda, how many people here know what a state channel is? Show of hands. All right, it's about a third. More advanced topics. How many people here know what a hash lock is? Okay, like a sixth. Okay, cool. So today I'm going to give a short overview about state channels, what they are, why we care. Then I'm going to talk about off-chain configurations of state channel applications, and then talk about what we're currently working on and goals for 2017. So what are state channels? Why do we care? So state channels are an application-level design pattern where you have transactions that are instant, private, and cost no gas. And it doesn't need any protocol updates. It's something that you build into your application. It's like the MVC of building dApps. And so it's a paradigm shift in decentralized application development, where you design your application to be off-chain first, and then use the blockchain primarily for settlement and verification. So one of the simplest applications that uses state channels is payments. So if you've heard of payment channels or the Lightning Network or Raiden, this is exactly the same thing. So the way a payment channel works on Ethereum is that some party A would propose a payment channel on a smart contract and deposit funds. Sometime later, some party B would join that payment channel and also deposit funds. Then they take it off-chain. From there, they can update the state without having to talk to the blockchain at all, just between themselves. And so you can see that the state is balance A, balance B with some nonce. The nonce tracks how many payments they've made to each other. And the verification for each update takes place off-chain, which means each party keeps track of all the payments that it's ever received, and it's able to double check that the other party isn't cheating. And if there is some kind of dispute, that's when you would go to the chain and present the latest mutually signed transaction as proof, and the blockchain would handle redistributing the funds. In the happy case, you would just present the final balances to the blockchain, and it will also just redistribute the funds. So we can make several optimizations on payment channels. The first is that we can have bidirectional netting channels so that the parties can send each other payments in parallel. So in the previous example, I was sort of talking about payments that are done in series, where party A sends party B some payment, and then they send some payment back, and there's this sort of agreed upon state, which is their balances. When you have bidirectional channels that use netting, what you're basically doing is allowing each party to send transactions in parallel and just keep track of how much they've sent and how much the other person has sent. And so you might accept a total payment of up to 500, even though the other person has only deposited 100, if you have, over the course of the channel, sent them 400. And so you can just net as you go, and they can just never pay you more than you've paid them plus the amount that they totally deposited. And that lets you send payments really fast because you don't need an acknowledgement from the other party too. You can use another optimization, which is hash locks, for secure multi-hop payments. So Joseph Poon did a really good job explaining how this works in Lightning. I'm going to talk a little bit about it as well. So you use hash locks in order to prevent intermediaries from running away with your funds when you want to send money to somebody that you don't have a direct channel with. So if I am connected to B, and then I want to send money to C, and I'm A, then I can basically give B a transaction with the hash of a random string that I generate called the secret, and then reveal that secret to C, the person I'm trying to send the funds to, directly. At that time, B has no way of running away with the money because they would need to present the secret to the blockchain in order to claim their funds. So what do they have to do? They have to send the same transaction, well, the same amount with the same hash lock to C, and then C would tell them the secret which allows them to unlock their funds in the BC channel, so C gets paid, and then because now B knows the secret, they can unlock the funds in the AB channel and get paid as well. And so this also allows the transactions to be atomic, which means that either they all work or they don't. And then one last optimization is Merkle trees of pending locked transactions. So we know that going to the blockchain is expensive, sending lots of data to the blockchain is expensive. If you have a channel and you're sending money very quickly to many people, you're going to have pending transactions for each person that you're trying to send money to, and you have to keep track of these. And so instead of keeping the entire array of pending transactions and all the hash locks and amounts and nonces, you can construct a Merkle tree with a Merkle root of that entire array, and then just send that along with your transactions. And in the case that you are sending money through an intermediary and they want to go to chain to claim their funds, they only need to prove that you made a transaction that is in that Merkle tree. And that is much easier to do than including the whole array of pending transactions. OK, so we're talking about state channels and not just payment channels. And so state channels are the general form of payment channels, whereas payment channels are like cash registers. State channels are computers. And so one of the things that we can program our computer in our state channel to do is play chess. So I'm going to talk about the sort of easier configuration to play chess on a state channel. In this configuration, you would just have a chess contract on chain which understands the rules of chess. And what that means is it knows what a valid move is, it knows what an invalid move is, it knows when you're in checkmate, it knows when there's a stalemate, and so forth. And so party A would propose a chess game on that smart contract and deposit funds, and just like in our previous example. B would then join that chess game, deposit their funds, and the two would be able to make any number of moves off-chain until the game is over. And then they would present the final state of the game to the smart contract. It would determine the winner and pay them out according to who won. And so you see that there's only a small update to the relevant state, which is the state of the game, and that tracks where all the pieces are. And so they'll be able to, the players again do the verification off-chain, which means if party A makes an invalid move, B would be able to reject it and know that the move was invalid. And then if they decide to take that to the blockchain, then they can basically accuse A of cheating and claim their funds. So advantages of having the chess game defined just purely on a smart contract is that it is simple. And the disadvantage is that there is a long matchmaking time and frequent blockchain interactions. And so what this means is if I want to do matchmaking for a game that's on a channel, I have to, one, submit the join. So if I go back for a second, I have to submit the proposed chess game transaction and also the join chess game transaction, and both of these have to be mined. And that takes some number of block times to get the confirmations required. And it also means that the players have to create a new channel for every time they want to play a new person, which can cost a lot in gas. So we can make optimizations. So we can make it slightly better by having the players be able to play multiple games with the same player. And so that could be any number of rematches or any number of games at the same time. That's kind of better, but we can get even better by introducing a server that is a hub. And so in this configuration, the model has changed. And now we have a server that intermediates the game. And so it's still trustless. The server cannot cheat you. But the state channel that the players are entering, they enter with the hub. And it is more of a lobby. And so you can think of it as like you go to a chess website and you're playing on a server and you put in some amount of funds. And then those funds, you can basically use them for any number of games through that server until you're ready to close your account, and then you get the remaining funds back. And so this works pretty much the same way. You have a hub. It proposes a chess lobby on a smart contract. A and B would separately create channels with that hub, and everybody would fund their channels. And then A would propose a game, which in this case would be a sub-channel contract. And so what that means is A basically sends the hub a commitment that says, I am willing to engage in a chess game with the rules defined in some contract, assuming that you find a willing second participant to play this game with me in some amount of time. And so the hub would then broadcast this commitment to its network, and B would join the game, accept that, and say, I also agree to participate in this game according to these rules that are defined in some smart contract. And then A and B would make their moves off-chain, and the state in this case for A would be the balance that A has, the balance that the hub has put into their channel, and the sequence number, the nonce, and any number of current games that are being played. And so then each game would have the state of that particular game. Now, what makes this work is that basically the hub is agreeing to play both players. And they're willing to do this because they know that at the end of the game, they can't lose both games. So basically, they are willing to lock up their funds with either A and B because they know that at some point in the future, A or B is going to have to come to them with proof that says, I win. And they can turn around to the other player and give them the same proof and then claim their funds in that channel. So there are advantages to using a hub, and the advantage is that you have faster matchmaking. And so the whole commitment of, I would like to play a game against X, if they play a game with me, using some rules, that all happens off-chain. And you can also resolve cheating and end games off-chain. If you agree to play by some rules, then if somebody makes an invalid move, then you can claim their funds immediately. You don't have to go to the blockchain for that. You do still have to go to the blockchain to resolve disconnection disputes. I'll come back to that. But the disadvantages for this are that the hub has to match the player deposits. So if A wants to deposit 100 Ether in their channel, then the hub also has to deposit 100 in the channel with A, and the same. And so the hub has high capital cost. And it's also more complex to build. So one of the problems with matchmaking is that you would think that you can only play games against the people who are connected to the same server that you are. That's not actually true, because you can play games against people who are connected to other hubs, so long as your hub has a channel open with that hub. And so what you end up with is a scenario where like A is playing hub 1, and then hub 1 is mirroring their moves with hub 2, who is actually representing player B. And so you have this chess game that's going back and forth, and that basically allows you to, if the hub is willing to put up an additional deposit with other hubs, then you can have this sort of chess network. One other way of doing this, another optimization, is to use trusted oracles for arbitration. So chess is a nice example because everybody understands the rules of chess, and it's relatively easy to program onto a smart contract. You wouldn't be able to program the rules of, for example, Halo onto a smart contract. And so if you wanted to play competitive Halo in a trustless way, you would have to use some trusted third party that is running the computation. So maybe someday you'll be able to program Halo in Solidity, but until then, you have to use a trusted oracle. And basically what that means is you trust some server to arbitrate disputes and to say who wins the game and so forth. And you can create a market for that type of trust. So if somebody turns out not to be a good actor, then you can move on to other hubs. All right, so can we do better than chess? And so if state channels are actually a computer, then we can program them to do anything. And so in this model, you have a hub still, but they propose a general state channel. And what that means, it's a multi-sig contract on the blockchain that can create other contracts and use those to arbitrate any disputes or to verify any type of transaction. And so A and B would then create channels with the hub on this multi-sig contract. And then A would propose some subchannel contract, which can be anything. It can be chess. And so when A does that, the hub would do the same thing. It would broadcast. It would say, hey, I've got this person who wants to create this contract with somebody. If you're willing to join in, do so. And they do. And then you have any number of subchannels. So if you go to the state, you see you have the same thing, except now you have some number of subchannels and the state for each of those subchannels. Sorry. And so now A and B close the subchannel through H. And so essentially how this works is the players can, or the participants in this sort of general state channel network can send their state to the hub, and the hub would be able to, or to the contract that is that they have with the hub that is managing their state channel, and then if they want to dispute some state, let's say one of their subchannels, that smart contract would take the state that they have for that specific subchannel and then send it to the contract, and that contract would be able to arbitrate. And so because you can program contracts to do anything, you can program your state channel to do anything. And so advantages to this are that you get this sort of off-chain smart contract network, and that also you have any contracts that you have that are in state channels can be pretty easily upgraded. Because either you just can agree in the channel to be governed by new rules, or you can just close the channel and start a new channel that is governed by the new rules. Disadvantages, again, are hub capital cost and centralization pressure. So, OK, moving on. Let's talk about what a Dapp looks like to a state channel hub. So once you have this sort of general state channel hub, each Dapp can be thought of as a protocol. You have two main functions, which are state transition and verification. And the contract logic needs to be implemented twice if performance is critical. And so this is basically similar to how precompiles work. And so basically the ways to run applications quickly is to precompile it. Worse than that is to just use the Ethereum EVM or JSON RPC and communicate that way. So if performance isn't absolutely critical, you can use that. The hubs also need to run off-chain code modules for each application that they want to run. So the logic that needs to be implemented there is when you need to go to chain in response to certain events, for example, to prevent replay attacks. If somebody is presenting a previous valid state, but it has been superseded by new states, then you need to respond and close the channel with them. Other applications, for example, Raiden, would need to search a network graph in order to find the optimal path to the target recipient of a payment channel transfer. If you are running sort of arbitrary code on these hubs, you have the halting problem. How do you know if the code that you're running is going to stop? And so you can have a situation where hubs just basically whitelist these decentralized applications that are running on state channels, and you get specialized hubs for specific verticals like finance and healthcare and Internet of Things and ad tech. And the hubs, to make it easier for application developers to launch dApps that they are using, can have DSLs, domain-specific languages, or template contracts where they already know that everything is secure, and you're just sort of configuring a few parameters. So I'm going to talk about current projects. We're currently building a real-time data exchange. And so the way this works is, say you have some stream of time series data. You want to be able to sell it for micropayments. And so you can advertise it on the blockchain, and people can subscribe to this stream and deposit some funds, and then send you micropayments in exchange for the stream of data. You can have a network of aggregators or data brokers that manage these streams. And you get the verifiability by using basically hash chains. It's a similar concept to how the blockchain works. If you wanted to periodically checkpoint data to the blockchain to be able to prove at a later time that it has not changed, you need to just submit a hash of that data. If you're using a time series data and you don't want to keep the entire time series in memory when you want to checkpoint it, then you can compute the Merkle root of just some piece of data and then recompute the Merkle root for every subsequent time series of data so that once you have that final Merkle root, you submit it to chain and use that hash to verify, because somebody would only ever be able to recreate that hash if they have the entire set of data that led to it. And you can tie that in with the settlement cycle of the micropayments so that you get your payment once you've put the proof on the blockchain of that piece of data. So our first implementation partner for this is Vidroll. What we're doing with them is allowing advertisers to basically sell data to each other. You might have noticed when you're browsing the internet that there are lots of redundant trackers to track your impression data on every website that you go to. And the problem there is that nobody in the ad industry trusts each other. So if you can prove that you have not tampered with the data, then you can have one tracker, and then everybody can just buy from that one tracker, and that'd be great. We're also building a transparent supply chain, and so this is closely tied to atomic multi-party transactions. Basically, you want to, if you are the supplier of something, be it retail, be it data, you want to be able to send it to somebody in the same way that we have in the Raiden network, in such a way that only upon the final receipt of whatever you're sending, everybody that was an intermediary in that transfer gets paid. And so this also allows you to have faster settlement times because you're dealing in crypto. And settlement because you're not waiting for the last party to send you the money so that you can send it to the next person. It's all just happening instantly. Again, first implementation partner, Vidroll for this. They want to put advertising supply chain all on the system. And so when you have real-time bidding, you go to a website, you have 200 milliseconds before you need the ad back, and in that time, the publisher would send everything they know about you to some supply-side aggregator who would then send that information to an exchange where a bunch of demand-side aggregators would bid on you on behalf of their advertising partners like Coca-Cola or whoever. And what they want is they want to be able to only have this whole chain of payments actually execute if the impression on the ad that was sold is valid. And so there's a lot of ad fraud on the internet, and there are safety vendors who track impressions. And so if you are able to, basically if the safety vendor signs off that your impression on said ad was valid, then all of the payments would execute. So you get this nice supply chain model. And I think both the supply chain and data exchange are going to be useful in other contexts too. That we're just starting there. We're also obviously working on the Raiden network, estimated MVP for developers, ready at the end of Q1, so end of March. And so the state of the Raiden network is that the protocol implementation is largely finished. Now we are dealing with ways of making it more robust. What happens if one node crashes? Well, we want to be able to restart events that have happened, so you need a write-ahead log so you can replay the messages. And basically thinking through stuff like that. And they are hiring, especially distributed systems engineers. So if that's something that interested you, you should reach out. I also want to highlight Machinimi, which is a great Node.js peer-to-peer micropayments middleware. It's in developer alpha right now. You can check out the link on GitHub. So goals for 2017, broadly speaking, is a production-ready Raiden network, the MVP of the real-time data exchange, a prototype of the off-chain smart contract network hub, and dApps that go along with that, and more implementation partners for State Channel's products. So if you're interested in State Channels for your business, definitely reach out. Any questions?
Thank you. Oh, we got one. We got two.
Hi, thank you. Could you explain how hash locks work across? I know you explained it a bit, but could you perhaps reiterate or go a little bit more in depth into how hash locks help in securing like multi-hop transactions in state channels?
Okay. Yes. So I'll probably repeat myself a little bit, but whatever. So if I am, say you have A, B, and C, where A and B have a payment channel, B and C have a payment channel. A wants to send C, let's say, 1 Ether. How do they do that? Well, they would generate a random secret, let's say it's cat, and then they would generate the hash of cat, and then they would send a transaction to B, which says, hey B, I will pay you 10 Ether, assuming that you know the secret that hashes to cat, or the hash of cat. So if you know cat, you get the money, right? Then B would go and send C the same amount with the same hash lock. In a private communications channel, A would then, going around B, would send C the secret, which is cat. Having received both a transaction from B that says, this is valid if you have the secret cat, then C can basically do one of two things. In the happy case, they will just go to B and say, hey, I have the secret, and B would be able to verify that it is accurate, because they know the hash, and then B would unlock the funds that are intended to C. And then B would basically do the same thing to A, and then get their funds. In the unhappy case, C can go to the blockchain and prove that they have both a transaction from B that says that they can have the money, if they have the secret, and they have the secret. And so if B refuses to unlock the funds in the forward direction, C can just go to the blockchain at that time.
Cool, thank you.
Yeah, and B can do the same thing. Yeah.
So when closing a state channel, there's a challenge period that needs to sort of allow someone to say if the other party was dishonest. So can you kind of walk through how that process would look in Raiden?
Yeah. There is a challenge period, and it allows you to, okay. So the reason you have a challenge period is because I can submit a state that is invalid. So if we have 100 transactions, and I initially deposited 100 Ether, and every time we had a transaction, I sent you an Ether, then maybe I only want to send the first transaction to the blockchain to close the channel instead of the 100th. So what happens is if I do that, then you have some period of time, which is the challenge period, to send in the 100th. And so the blockchain doesn't know that there are more transactions, it only knows what you tell it. And so once the challenge period has started, you are able to send in this final transaction and actually close the channel. And you can actually enforce a punishment on somebody for trying to close a channel and lying, essentially. We call it executing a replay attack. And so you can just charge a deposit to close a channel. And if you were wrong, then you lose the deposit.
So how large is the deposit, and how long is the challenge period, or is that something that can just be adjusted?
That can be adjusted.
Okay.
Yeah. It's configurable. I think in Raiden it's a few minutes. Could be wrong.
We have time for one more.
There is a DDoS vector, though. You only have so long to close a channel, so yeah.
Yeah, is the Raiden project created by consensus, or how is the relationship between consensus and the Raiden project?
There's no official relationship. We're good friends. I was in Berlin like 2 weeks ago, hanging out, helping, got my tests running on my machine and stuff like that. Been making contributions.
All right, thank you very much.
Yep.